This last example, we're going to take a quick look at a Tic Tac Toe game. And so if we run it, it's basically going to display the board here. And let's step through the code. All right. So very first thing in our main function, this is what's getting invoked or called, right? We call main. And then from main, everything else happens in the game. So we have a one-dimensional array here. This is going to be our tic-tac-toe board. And that's what's getting drawn out here, okay? And so we will have indexed positions on the board for 0, 1, 2, 3, 4, 5, 6, 7, 8 to represent the 9 squares under which we can move our pieces. We'll have a player piece and a computer piece and something to represent the current player. And of course the number of squares, which is 9. All right, so we're going to call the method or function introduction, and that function returns a value. And when it's done, we'll know who's going first. Is the computer going first, or is the player going first? Okay. So let's jump to introduction, see what happens. We have a couple of locals, first or second, intelligence, and player piece, okay? And here's what we're going to do. We're going to display the rules and the board. Computer will play as your opponent in this game, and then while intelligence is not equal to I, and intelligence is not equal to S, and this is just another way of controlling user input. We want to keep this while true loop looping till they give us a valid answer. Do you want your opponent to be intelligent, or do you want them to be simple-minded? You know, or so they choose that option, and all that's going to do is that's going to affect the routines or the algorithms that we use, you know, in code, or the AI that the game uses to play against the player. So we can only use a few, or we can use them all, which would be a more intelligent opponent. Okay. And so we're going to get the user's choice, convert it to lowercase, pass that into intelligence. And then based on that, we'll set the value of, you know, global, in this case, easy to be false or true. All right. So in this case, if they, you know, if they choose an intelligent opponent, then global easy will be false up here. And if they choose a simple opponent, then easy will be true, okay? Then first or second, and this is what, you know, we want to return. Do you want to make the first move? And we're going to get that from the player, convert it to lowercase, pass it into first or second. We'll switch on it. And then, okay, you take the first move, or okay, the computer takes the first move. Either way. So if you take the first move as the player, your piece is X, okay? And if the computer takes the first move, then the player's piece will be O. First move is always going to be X, but we give the player the choice. We need a default in our switch in case they type something we're not expecting, some weird input. Here we're just pausing, you know, the console, but we do need to catch the return value. Even though we're not doing anything with it, we should provide null to catch it. When we get done, we're going to return player piece. And the player piece is going to be either what? An X or an O, based on whether they want to go first or whether they want the computer to go first. Okay? So then we go up here and we are going to call the display method or display function. We're going to pass in this array up here, game board. So let's jump now to that function and see what that function does. And then display, what does it do? It just takes an array of type character. Okay? So it takes that single one-dimensional array and it's just going to display. And then whatever is stored, whatever characters are stored in the elements of our array, those will be displayed when we display the board, along with the pipe symbols and these little dashes here, okay? So I'm just going to make my choice over here. I'm going to say intelligent. Okay, your computer opponent will be more difficult to beat. Do you want to make the first move? I'm going to say yes. Okay, so I take the first move. Your X, computer is 0. Press enter to continue. And here is where we call display board. See, it draws out the Tic Tac Toe board. And I choose a location 0 through 8. Well, let's jump back in the program flow. And, we're right here now. We've called display. We've passed in our array board. It's all empty. Nobody's made any moves yet. So then what are we going to do? We have a while true loop here. And this is sort of the engine for our game. But while CheckForAWinner is equal to no, so as long as we don't have a winner, and CheckForAWinner will return a winner if either the computer or the player has a winning move, in which case they have 3 O's or 3 X's connected vertically, horizontally, or diagonally. And then in that case it would return yes, we have a winner. But as long as it returns no, we don't have a winner, then this loop controls, it's sort of the game engine. This loop controls the flow of the game. Okay, so current player is equal to current player, and current player is what? And how did that get set? If the player piece is X, the computer piece is O. Otherwise, the computer piece is X. Well, X always goes first. So X is the current player. So current player, in this case, will be, the first time through, it's going to be X. If current player is equal to player piece. Okay, well, the player piece, we know that's how we tell the difference between whether it's the computer versus the human. Then we'll say player's move, okay? And what do we do? Choice is going to equal to PlayerPlays. We have to pass in the game board, and we have to pass in squares, right? The number of squares we have on the game board, 9. And the player piece, is it X or is it O? Okay? So that goes to PlayerPlays. Notice we pass in our arguments here, right? So here's our character array for our game board, our number of squares, which is 9, and our player piece, which is X or O, based on the player's choice. Human choosing location, and we're just displaying that text right here. And we tell them, choose a location between 0 through 8. And we're going to keep them looping here in what's called the LegalMove method. So the condition for this while true loop is while player's move is greater than squares or player's move is less than 0. So if they tried to move to position 9 or 10 or 11 outside the valid range, we're going to keep looping. And we're going to hold them here in this holding pattern until they give us good input, good valid input. So it can't be greater than the number of squares, which is 9, and it can't be less than 0. And it has to be a legal move. Or a legal move, in this case, is equal to false, okay? So if they tried to make an illegal move, well, what's an illegal move? How do we tell that? That's just a simple method here. We pass in the character array, the game board, and we pass in the move their choice. And all we care about is that square empty? They can't move there if either their player piece is there or if the computer's player piece is there. We can't let them move to a square that's already occupied. So all we care about is that particular element is empty. Okay? So we're just checking for a space there on LegalMove. Remember or says that it doesn't have to be, it's not the same as and. It doesn't have to be every side or on both sides of the and operator, but or says only one has to be true. So if any of these are true, if the player types in a number greater than the number of squares or less than 0, or if they try to make an illegal move, if that evaluates to be false or returns false, then what? We're just going to keep asking them, hey, you need to move, okay? You need to move, player, choose a move. And we'll give them a little bit of feedback here. If it's greater than squares or less than 0, hey, that's outside of valid range. And if legal move is false, we'll tell them, hey, you cannot choose that location. It already has in this case, A and then the board and the players move, okay? So, let me go back up here, all right? So that fulfills PlayerPlays, all right? So, and then finally we're going to return the players move, okay? You know, what is the players move? That's their choice, the choice of square that they decided to move to, okay? That's PlayerPlays. And let's go back up here. Okay, else. All right, so once the player makes their move, then, you know, what happens? PlayerPlays get, you know, it returns a value when it gets done. That's their choice. N is equal to choice. In this case, we're just getting the first character there. All right. And we have to shave off, you know, in this case, there's a little bit of extra character value that we need to shave off from read host. All right, so we do that here. That's all we're doing here. In this case, as an integer, we want to make sure that that string value comes in as an integer, and we want to shave off. We just all we care about is one character. So, you know, read host returns a string, but we don't need a string. We don't want a string. We just want a single character in this case to plug into or pass into our character array. And so that's n, and then we set it to be n, and then the player piece, whether it's x or whether it's o, okay? And this won't happen because that's only if it were the computer's turn. So this has happened, and so then what? We call the display board method again, right? And that's just going to display the game board. So now we'll display it with the player's piece on it. Okay? Does that make sense? And then, if current player is equal to player piece, it's just going to toggle back and forth. So if that was the player's move, then current player becomes the computer. We want to be able to switch back and forth. Otherwise, if it was not the player, if it was the computer, then the current player will become the human or the player. So here we're just toggling back and forth. We're switching every time we iterate through this outer while true loop. We're switching back and forth in this if-else block between the player and the computer, the player and the computer. Okay? So I'll make my move. Let's say I want center square, so 0, 1, 2, 3, 4. I'm going to choose 4, okay? So if I choose 4, it calls display board. Now it's the computer's move. Well, how does the computer choose? So we loop through this while true loop again, and the next time through, now it's the computer's move, right? So the computer calls ComputerPlays, passes in game board, number of squares, which is 9, its player piece, 0 or x, excuse me, the player's piece, 0x, and the computer's piece, 0 or x. Okay, so let's go look at ComputerPlays and see what happens. So ComputerPlays takes our game board as a character array, the number of squares, the player's piece, and the computer's piece. And basically, there's three areas we want to focus on. You know, how do we get our computer to act like a human, to play like a human against another human? We need to figure out how to translate the rules of Tic Tac Toe, you know, into code. And we need to figure out a way to how to translate that into logic, into a flow of logic, whereby our code can play against the player. So breaking it up into, you know, sort of compartmentalizing it or breaking it up into smaller pieces, you know, back to how do you eat that elephant. There's 3 main things that we need to do with our code to get it to be able to emulate a human player. So if the computer can win, you know, the very first thing our code needs to do is take a look at the board, and if whatever the player piece is for the computer, if it can win on the next move, it needs to make that choice. So if it has 2 X's or 2 O's, whatever it might be, and if by adding a third one, it gets 3 in a row, horizontally, vertically, or diagonally, that's what it needs to do. Okay? That's the first thing. But if it can't do that, if it can't win on that next move, then what's the next thing that it needs to do? Okay, well, if the computer can't win on the next move, then it needs to look at all the player's moves and say, is the player about to win? And if the player is about to win, it needs to at least block the player, okay? And then, if the computer can neither win on the next move nor block the player on the next move, if that's not necessary, because the player doesn't have a winning move, then the third option, the third best thing that the computer should do is choose the most advantageous position to place its piece on the board. And that's represented by this array here. So middle square, and then, you could change these numbers around to create potentially a more difficult to beat computer opponent, but these are just the one, or arbitrarily, these are just the squares I thought would be, give the computer the greatest chance of winning. So again, this logic is a three-step process, right? First, if the computer can win, if it has two of its player piece, and by adding a third one, horizontally, diagonally, or vertically, then it needs to do that and make its winning move. If it can't, if there's no winning move available, then it needs to look at the player's pieces and block the player if necessary. The player is about to get some. And then if that's neither the case, if it can't make a winning move and the player is not in a position to make a winning move, then it needs to choose the most advantageous square to position its piece to. All right. So let's take a look at these are the three areas of logic that we want our computer opponent to focus on. So how would we code that? So how can we translate that to code that whether or not the computer can make a winning move? Well, we have an outer for loop. Okay. So while x is 0, x is less than the number of squares, right? There's 9 squares on the board. And we'll prefix increment x this time. First, we need to make sure that it's a legal move, right? We need to make sure there's no player piece there or no computer piece there. It has to be a blank space on our board. Okay, so blank character. So if it's a legal move, and we're just going to go through and we're basically going to iterate through every single square. And if it's a legal move, see if it's empty. And okay, if it is empty, we pass in the game word. We're going to take the computer piece and we're going to check for a winner. And this function, we'll go look at it in a moment, but it returns true if it's a winning move. If 3 of the same piece get connected horizontally, vertically, or diagonally, it'll return true. Otherwise, it returns false. Okay? So if check for a winner, if the computer can win, then return x. And what is x? Yeah, that would have been the, that potential choice. In this case, that the computer chose. But if it's false, then undo it. Clear that space and don't make that move. Okay? And when you encounter the return statement, remember in the video on, several of the videos on functions, when you encounter that return statement, it exits the function, returning that value. So in this case, we just exit the function if the computer can make a winning move by adding its piece there. Otherwise, it blanks it and it moves on to the next area of logic. Okay, so the computer couldn't make a winning move, check for a winner, and then it moves on to this area. Well, let's take a look at check for a winner, and then we're going to come back to the ComputerPlays and look at these next 2 logic blocks. Okay, so let's go look at check for a winner. How do we check for a winner? Well, we pass in the game board and we pass in the number of squares, which is 9. And in this array here, this is all the winning combinations. All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Those are the horizontal winning combinations. 0, 3, 6, 1, 4, 7, 2, 5, 8. All right, so 0, 3, 6. Those are the vertical winning combinations. So you have 3 horizontal, you have 3 vertical, and you have 2 diagonal winning combinations, 0, 4, 8, and 2, 4, 6. Okay, so this array represents the tic-tac-toe board numerically over here. So we need to check for these. And if we have the same pieces, whether player or computer, horizontally, these 3, vertically, these 3, or diagonally, these 2, then we have a winner. How do we do that? Well, again, it's sort of one of those bubble sort issues. So if any has 3 values that are the same, we have a winner, and we can return X or a tie. So what do? We have this loop here, this for loop. Row starts out as 0. While it's less than total rows, we're going to prefix increment row, okay? Total rows is 8. What does that represent? It's the number of winning combinations, right? 3 horizontal, 3 vertical, and 2 diagonal. So 8 is the number of winning combinations. All right, total rows here. Could also use winning rows.count, but if we wanted to, but anyway. So in the if block here, what are we testing? What are we checking? If the board and winning rows, row 0, if it's not equal to blank. So to make sure that it's not blank, it has to be something there. And it equals if, in this case, the first element that we're checking is equal to the next element that we're checking in row, and the third element that we're checking is equal to, all right, so this is compound. This has to be true on this side, and this has to be true on this side. So it's not blank, and what else? Okay, so board winning rows, row 0, the first column, is equal to board winning rows, row 1, and board winning rows, row 1 is equal to board winning rows, row 2. So we're checking that the player piece is what? That's this first element here, right? So do we have a connection? Do we have the computer or the player's piece that's 0, 1, 2 horizontal, or 3, 4, 5, or 6, 7, 8? And as we iterate through this loop and we change the number of rows, we're just checking the winning combination as we go down. Do we have a winning combination here, here, or here horizontally? Do we have one here, here, or here vertically? And do we have one here or here diagonally? Okay, so does that make sense? Understand? Okay. So that's all we're doing here in this block of logic. And if we don't have a winner, well, if we have a winner, what's going to happen is we're going to return the player piece that is stored at that location, whether it's an O or an X. Remember, when we hit the keyword return, we exit the function. That's it. Okay, so whether it's an X or an O, that's the winning combination. We will return that. Okay. Otherwise, what happens if we get all through that, and if in this case, what if we don't have any empty spaces left? In this case, it'd be a tie, right? So no empty spaces is true. Well, we set it to be true, and then we're going to go through the number of squares, which is 9, and we're going to say if any of those is still blank, then no empty spaces will be reset to false. So we don't have a tie, we can still keep playing. But if it doesn't get reset to false, if it remains true, then we return T because we have a tie. Okay? Otherwise, nobody wins, and it's not a tie. So here, if O or X won, we would return O or X. And here, if we had a tie and there were no more empty spaces left, we would return a T. But typically, normally, we're going to return an N until we have a winner or a tie. Okay? Does that make sense? Okay. So, back to ComputerPlays. So now we understand what goes on in CheckForAWinner. And now we understand the very first thing the computer did was it said, hey, I'm going to repetitively, I'm going to test every combination. And if my piece, my player piece, can win horizontally, vertically, or diagonally, I'm going to make my move there. and win the game. But if not, okay, now the computer has to look at the player and say, what is the player doing? And if the player is about to win, I need to block the player, okay? And here's where we have our global. If global easy is equal to false, well, we turn this off, and we won't even block the player if they choose to make their opponent simple. That makes the game a lot easier, but normally, if they don't turn that off, and their opponent is more intelligent, well, now the computer's going to look at the player piece, okay? So y starts out at 0. It's less than the number of squares, which is 9. Prefix increment y. Is it a legal move? Is that space empty or not? Return that. In this case, make sure that the computer's or the player's piece is not there. And if it's empty, then we're going to take it and we're going to position on the board the player's piece, okay? So the computer's manipulating the player's piece, and it's going to go through every combination of those winning combinations and check for a winner. We've already gone over that function. But now, instead of checking for itself, it's checking for the player. Can the player win horizontally? Can they win vertically? Can they win diagonally? Right? Through the data that's stored in that array and check for a winner. We have all the winning move combinations. Okay? And in this case, if it returns true, if the player piece, if they can win there, then we're going to just, no new line, and we're going to return y. And y is the position on that board where the computer's going to place its piece there to block the player, okay? And then we would exit the function, exit the method, okay? Otherwise, if that's not a winning move for the player, we're going to keep looping and cycling through this loop here, looking at all the different possibilities for the player. And we need to undo that. The computer is comparing, and it's looking at all the positions on the board and trying to figure out whether or not the player can win on the next move. And if so, it's going to block the player. But when it's done, it needs, this is just a simulation. It's just simulating the move. You don't want to actually, put a piece there and fill up the board. So we're going to blank it, convert it back to a blank space again. Okay? And so we check for a winner if the computer can win, and we check for a winner if the player can win and block them if necessary. And then if neither one of those, give us, if the computer can't win on the next move, and if it doesn't need to block the player on the next move, then what? Then we jump down here and our preferred choices, the number of, the squares we want to position our pieces in, and I starts out at 0, while it's less than the number of squares, which is 9. We'll go through preferred choices, okay? And if it's a legal move and it's not blank, if it's a legal move and it's blank and there's not a computer or a player piece there, then we'll position the piece starting with the center and then moving into what we believe are the most favorable squares, okay? And again, we'll return choice. So if we do that, that's what happened. I made the move here on X as a center square, and then the computer decided, well, it's looking at these moves, and the first time through, it can't win because it hasn't even moved yet. This is its first move, all right? So it jumps down here to this next block, block 2. And in this logic, it says, can I win? No, I've only got one piece on the board. Okay, so now it jumps down here and says, well, neither I can win, nor do I need to block the player because the player can't win. So what's the next most advantageous thing to do? Choose the center square, but it can't choose the center square because I already chose it. All right? And it's not empty. So then the next thing it does is it chooses 0. You see this? And the computer chose 0 up here. Okay? Does that make sense? Okay. I'm going to go back up to main. So we've gone over the important functions and methods: display, check for a winner, PlayerPlays, ComputerPlays. We looked at all that. Finally, we're going to look at DisplayWinner. What does DisplayWinner do? Then we're just going to pass in the winner once we determine there is one. the computer piece, the player piece, and if the winner equals the computer piece, hey, the winner in this case wins the game. The computer wins this match. Sorry, you lose. And that would be either 0 or X, depending on which player piece the computer had, based on the human's choice, right? Based on the player's choice when they began the game. Let's say if the winner is equal to the player piece, then the winner wins the game, so X wins the game. Excellent, you win this match, the computer loses. The only other possibility is a tie, right? If T got returned, there were no more empty spaces left, and there was a tie. So let's go back up to main. And then after we do that, we would say game over. So let's go ahead and play the rest of this process through here. And I'm going to choose 2 up in the right top corner. Okay, and now the computer blocks me. In addition to blocking me, it can make a winning move here if I don't block it, right? So 0, 1, 2, 3. If I don't put anything there, then the computer would win. So I need to block the computer now. So I'm going to put, okay. And then when I did that, the computer had to block me, right? Because if the computer didn't move here, I would have won. And it's following that second logic block, okay? And at this point, looks like we're going to tie. There's no real winning combination unless I just ignored what the computer was doing out here. But even then, I'd have to add my position, my piece there. So let's do 7 here. I want to go to square 7. I choose 7. Okay. Well, and the computer chose, in this case, position 8, and then I can actually win if I go 0, 1. So if I go 1 there, X wins the game. Excellent. You win this match, and the computer loses. Okay. And let's run it again. And let me choose I for intelligent, and I'll let the computer make the first move. I'll say no. Okay. So computer chooses location 4, right? Remember that was its most preferred or preferable location. I will choose location 0. And okay, looks like it's got a win there. And let me try to block it. So I'm going to position 7. And in this case, the computer wins this match, right? So yeah, it computed and it figured out that was a winning move. Okay, so hopefully that kind of illustrates how we would translate this project into code. And I know you could make a more creative, more interesting, and more challenging Tic Tac Toe game. So this is my challenge to you. This is your mission, should you accept it. I want to see your Tic Tac Toe game. I want to see your ideas translated into code. I want to see how you would paint this game with PowerShell. Have fun.